All right, in this video, we're going to talk about post estimation in OpenCV using Python. So we will start off by saying what it is, why do we need it, how does it work, and jump right into a coding example. So by the end of this video, we will see how we could draw this cube here on the right on top of our calibration images. So what is post estimation? The idea is finding both position and orientation of an object in a video or image or video. So why do we need post estimation? So we have augmented reality, you have activity recognition, film and animation, and many other examples. So how does post estimation work? You have the idea is you have world points are projected onto the image plane. So here are your world points and it gets projected onto your image plane. And we are trying to find the position and orientation that minimizes the reprojection error. So you may have the true point here, and then you have like a projected point here, and there could be some error, and you might have errors between all the points. And we're trying to minimize what that error is. Okay, so the idea is you have your image points and you have your world points, and you have some transforms that relate the two. You have your intrinsics, you have additional matrix here, and then you have your rotation and translation, which capture your extrinsics. So all of this combined will give you your projection matrix that brings your world points to your image points. And then from there, you could rewrite it into a more compact expression here, as you see down below. So the idea is we want to estimate in OpenCV, we call it as RVEC and TVEC, and then those are the actual parameters that we're trying to find. Okay, so there's typically different solvers that are out there. You have um, here we have the solve PMP iterative. So this is the default one that we'll use, but then there's some other ones too, which we won't go into too much detail with, but for the iterative one, you have the what's called a Levenberg Marquardt. And what this does is it takes like the Jacobian and does like a Newton type of method of minimization error. So if you have like a function here, and then you're essentially trying to get lower and lower and lower until you find the minimum. So this is like a two-dimensional case, but you expand this to a multi-dimensional case using what's called the Jacobian. But essentially it comes down to minimization error by looking at the gradient at each time step. So that's the general idea. And then you also have like DLT methods, which tries to solve like least squares directly. Some methods uses like SVD and so on. But you can see part two, you have some other different methods that you can explore. But usually the default one works fine. So that's the one we will use in our example. So let's jump right to it. Okay, so here is our post estimation script. We import some of the modules that we need, and we're going to declare an enum of two types because we're going to be drawing axes and cube later on. So we made an enum for that. And we have a draw axis function here, which we'll use, and I'll explain in a bit. And same with the draw cube, which I'll explain later. But the main program we're running is called the post estimation function. So what this function does is it's going to take the draw option based on what we're drawing. And what we want to do first is retrieve the camera calibration that we obtained in our previous video, pull it out from the script, the calibration.mpz file, and then read in the values and store it as the cam matrix and distortion coefficient variables. So after we do that, what we want to do is get all the paths for our images. So I think this might make more sense if I say obtain image paths here. So we're going to get all the paths for the images. And then what we want to do is set up our termination criteria, which we talked about before. So here we have the EPS and iteration. So that's the error and number of iteration count. And then same here is if we take a look at this, we set up to have the number of our error and iterations that we set. So we take our world points here, and from our world points, what we do is we assume some location in the world space, and then this step here is we're going to try to reshape that into an array, into the structure that's going to work for our functions later on. Okay, so what we want to do here is to find some axis points. It's just arbitrary points in the world space, And then we want to find cube corners, which are more points, the 8 points of the cube. And those will be used to project from the world points into the image plane later on. So the steps here is similar to camera calibration. We find the corners. So we read in the image, convert it to grayscale, pass it into the find chessboard corners. We find the corners. Okay, so after we find the corners, call corners org. After we find that, we refine it using the corner subpix function, which we talked about in the camera calibration. And then the new function here is called the solve PNP. Okay, so the solve PNP function, what this does is it finds the rotation and translation vectors, which is here, and we'll use that to do some of our projection later on. So what this takes in is the world points. Um, Here is called object points. So that's going to be an n by 3 array. You have your corners refined, which is a n by n numpy array. Your camera matrix, which is going to be a 3 by 3. And then your distortion coefficients, which is a 1 by 5. So based off of our drawing options, first off, we're using the axis. So we have our project points function. So what this one does is it'll take in our object points, which here we're calling axes. You have your rvec and tvec, and then you pass in the camera matrix and your distortion coefficients. And then what this will return is your image points, which will be an n by n array, and then the Jacobian, which we're not using. So we call the draw axis function that we've defined up on top. So what this does is it'll take your image, your corners, and your image points, and then it's going to draw the lines onto the image. And one thing to note is we need to do some conversion to make sure that all the points are integers. So that's what we're doing. And then we do the RGB for the different axes, which is what these different color codes are for. So if I go ahead and run this program, we could see our axes being drawn. So if I run this, you see we have our axes drawing for each of the image, for a calibration image that you have. So you can see that my camera is rotating and the axes are adjusting accordingly. So that tells us that our calibration is looking pretty good. Okay, so now if I take a look at our next step, so here is our cube implementation. So the only difference, everything else is the same. We have a different option here for draw cube. So we're going to project it, but now with our draw cube function, it's a little bit different. We're going to read in our image points. We're going to create a contour, which is going to be the green plane. And then for each of the uh, corners on our cube, we're going to connect the dots and draw the borders of our cube. Okay, so if I go ahead and run this, we will see our cube being drawn with the plane where it's on the chessboard. Okay, so you can see all the images is adjusting accordingly to the translation orientation, just like we want. Okay, so if you found this video helpful, give a like and subscribe, and I'll see you in the next one.